This video will be the last section of our discussion on solving systems of linear equations. Again, we are finishing up our discussion of iterative methods to solve linear systems. And in particular, we're going to talk about a very brief introduction to the idea of relaxation, or sometimes called successive over relaxation, or SOR. Relaxation is a method that can be used to speed up convergence of various iterative procedures, such as the Gauss-Seidel method. After each new value of x is computed, that value is modified by a weighted average of the previous estimate and the current estimate, as shown by the expression here. The weight, or relaxation factor, omega, is chosen such that it is between 0 and 2. If omega is equal to 1, then the method is exactly the original method, for example, the Gauss-Seidel method. We can rearrange the equation to illustrate the effect. So if we define delta xi as xi at iteration k plus 1 minus xi at iteration k, so that xi at iteration k plus 1 is equal to xi at iteration k plus delta xi. So our new value is equal to our old value plus some change delta xi. Relaxation alters the amount of change delta xi that is actually added to the old value. So xi at iteration k plus 1 is equal to xi at iteration k plus omega times delta xi, where omega varies between 0 and 2 and is called the relaxation factor. So if we think about the Gauss-Seidel method to calculate our new value, and before applying any relaxation, our estimate of our new value we can call the Gauss-Seidel estimate. With under relaxation, omega is between 0 and 1, then the method gives a new estimate that is somewhere between the old estimate and the Gauss-Seidel estimate, so it decreases the step size between iterations. This can be used to speed up convergence in the case of oscillatory behavior by dampening the oscillations. And it is also possible to make a divergent computation converge. Over-relaxation, or sometimes called successive over-relaxation, or SOR, occurs if omega is between 1 and 2. In this case, extra weight is placed on the new estimate, so we're increasing the step size between iterations. This helps to reach the solution faster in the case of monotonic convergence. So in the case of monotonic convergence, the assumption is that the new estimates are moving closer to the solution. So if we over-relax, apply extra weight to the new solution or the new iteration, then we'll move towards our solution faster. And no relaxation occurs when omega is equal to 1, and we just have our original method. So this can be shown graphically in one dimension. So here we've got the number of iterations and the estimate of our variable x, and the line here is showing the value of our solution that we're interested in, xr, for example. So without relaxation, with monotonic behavior, we may have something that looks like this. And then when we add relaxation, we can get that to converge faster by moving towards the solution quicker at each iteration. If we had a solution that originally had oscillatory behavior, like in the example shown here, so the blue line, adding some under relaxation, we're able to dampen those oscillations, for example, like the red line, and we can even get monotonic convergence if we really overdamp the oscillations, like the orange line here. So in both of these cases, we're able to speed up the convergence by applying relaxation. Now, the optimum value for a relaxation factor is highly problem-specific, and it is often determined empirically. For a single solution of a set of equations, finding the optimum omega is often unnecessary. However, it may be worth finding if the problem will be solved many times with similar parameters. So, depending if the solution has monotonic behavior or oscillatory behavior, increasing or decreasing our omega will lead to either a greater number or lower number of iterations required for convergence, and there is some optimum omega for a particular problem, which you may want to find, but in many cases it is not necessary to find the optimum.